Hello everyone, thanks for joining me today. So in our first video here we're going to talk about algebraic properties of complex numbers. Before we get too far along with that, I just wanted to maybe talk about some things that I suspect that you already know. Most people have been exposed to imaginary numbers and complex numbers at some point in some sort of pre-calculus level class. So let's see if some of these things make sense. So first of all, you've probably seen before that the imaginary unit I is defined to be the square root of -1. And while that's certainly true, we're going to take a slightly different approach as we start this class so that we don't have to think so much about what do you mean the square root of -1? Because, when we use the symbol square root, it confers some meaning of, well, when you square a number, you get -1. Or, the square root of any number is the number that you square in order to get that number back. And it's usually associated with real numbers. So anyway, we want to try to avoid some of that weirdness. And then the idea of complex numbers is sort of like fusing together real numbers and imaginary numbers in the following way. So complex numbers look like x plus I times y, where x and y here are real numbers. So for example, z equals 3 plus 1/2 I would be an example of a complex number. And of course, you can add and subtract and multiply and divide complex numbers in sort of ordinary ways. For example, 2 plus 3i plus -3 minus 5i. Well, the idea would be here is you just add like things, right? So you'd add the real numbered part of the expression, and then you'd add the imaginary parts together. So you'd get 2 minus 3 for the real part, and then 3 minus 5 for the imaginary part, or -1 minus 2i here. And if you wanted to multiply them, something like 2 plus 3i multiplied times -3 minus 5i, well, you would just sort of, as they say in high school, you'd FOIL it out, right? So multiply the first terms, you get 2 times -3, multiply the outer terms. So really what you're doing here is just distributing. So 2 times -5i, then you multiply the inner terms, 3i times 3, and then you multiply the last terms, 3i times -5i, and then you would simplify that expression. But anyway, you've probably worked with complex numbers on this sort of level before. And maybe you've even seen that you can represent complex numbers as points in the plane. So I could put down a coordinate system here. And if we looked at the complex number, say 3 plus 2 times I, the way you would represent that in the plane would be 3 along the x-axis and 2 along the y-axis. We usually call that the imaginary axis. And then your complex number would be this point right here, 3, 2 in the plane. So what our goal is to sort of lay down the foundation for complex numbers in a way that's very precise and rigorous without having to think too hard about what do you mean by the square root of -1. And we don't want it to seem like something that's mysterious. We want it to just be straightforward. So the easiest way to do this that I've seen is to just define complex numbers to be ordered pairs. So here we want to build the complex numbers from scratch without assuming any sort of weird things like, oh, square roots of -1 and that sort of thing. Seems too mysterious. As a set of points, we're going to define the complex numbers to just be a collection of ordered pairs where both of the components are real numbers. So formally, the complex numbers as a set of points is just R2, the real plane. What's going to make the complex numbers different from the regular real plane is the two operations that we will define on this set of points. If you start with two arbitrary complex numbers, z1 equals x1, y1, and z2 equals x2, y2, then the way we're going to define the sum and the product is the sum will just be component-wise addition. So if you add z1 to z2, you're going to get x1 plus y1, x2 plus y2. Now it's multiplication that really makes the complex numbers the complex numbers. So the multiplication here is going to look a little strange, but it won't seem strange when I show you what we're really doing. The product of the two complex numbers would be x1, x2 minus y1, y2, x1, y2 plus y1, x2. Well, that's a strange looking way to multiply 2 points. But we'll see shortly that it's a pretty natural thing to do. But for now, let's just say, just go with it as a formalism. Okay, someone defined this strange multiplication, and let's see how it works. So in this example that I have here, where z1 is equal to 1, 3, and z2 is -1/2, 4, we could easily do the sum and the product of these 2 points. So z1 plus z2 you just do component-wise addition, and you'd get 1 minus a half and 3 plus 4, or simplifying, we'd get 1/2, comma 7. And then z1 times z2, okay, so I'd do x1 times x2, so 1 times negative 1/2, and then minus, then you do the product of the y components, so minus 3 times 4, comma, then you do the x1 times the y2, so that'd be 1 times 4 plus, and then you do the x2 times the y1, so that'd be negative 1/2 times 3. And of course you could simplify that down a bit. Let's see, whatever, negative 1/2 minus 12, I guess that'd be negative 25 halves, and then you'd have 4 minus 3 halves, so 5 halves. Okay, so moral of the story here is that addition and multiplication of complex numbers is not that complex. Little pun there. A few basic definitions and notation and terminology here. So first thing, we want to talk about the real and imaginary parts of a complex number. So the real part of a complex number is just that first component. So if z is x comma y, then the real part of z is just x, and the imaginary part of z is y. And then, of course, anytime you have some set of things, you got to talk about what you mean by equality. So when we're talking about complex numbers, two complex numbers will be equal. Well, we just want it to be that they're the same point, right? The same ordered pair. So that just means that we need their corresponding components to be equal. And the real part's the first component, and the imaginary part's the second component. So z1 would be equal to z2 if and only if the real part of z1 equals the real part of z2, and then we want those second components to be equal, so we need the imaginary part of z1 to equal the imaginary part of z2. The way that we defined complex numbers didn't involve this concept of square root of -1 at all. It was just, here's some ordered pairs, those are the complex numbers, and here's how you multiply them and add them. And nowhere in that definition of multiplication or addition did we have to even confront the possibility of doing the square root of -1. It was just ordinary arithmetic. So now we want to move away from that ordered pair notation and get back to where we have that concept of I, but without the weirdness of thinking about it as square root of -1. First thing we're going to do is when we have a real number, let's say x, we're going to denote the ordered pair x comma 0 as just x. So the idea here is, from now on, if I just write x and it's understood x is a real number, that really means in terms of our complex numbers, which are all ordered pairs, that I'm talking about the ordered pair x comma 0. And then the next thing, I want to talk about scalar multiplication. So scalars are real numbers, and I want to talk about what does it mean when I multiply a real number times a complex number. In this setup, c is a real number that we call a scalar, and z is x comma y, that's a complex number. So whenever I do c times z, of course that's going to work out to be just what you would hope it would be. It's going to be cx comma cy. I'm not defining it that way. This is actually a consequence of the way we've previously defined things, because we've already said what it means to multiply two complex numbers. Now we're thinking of c here as a real number, but we know that a real number can be represented as a complex number, like what we've done in green there. So the reason this makes sense to do scalar multiplication this way, as cx times cy, is that formally c times z would be the ordered pair c comma 0 multiplied times the ordered pair x comma y. And then we have a definition of multiplication for ordered pairs. So remember, you do it this way. You do c times x, so you multiply the first components, then you subtract, then you multiply the second components, so 0 times y, comma, then you multiply c times y, then you do plus, the second component of the first ordered pair times the first component of the second ordered pair, which of course works out to just what we wanted to, cx, cy. So scalar multiplication works just like it did in, linear algebra class when you multiplied a vector times a scalar, which is good because we're going to start thinking about complex numbers as vectors in a little while. Now we're going to define what we mean by I, and I don't think you'll be surprised by what we mean by the imaginary unit I, but it has to be an ordered pair, right? And the ordered pair that we're going to define I to be is 0, 1. And we also talk about what are called pure imaginary numbers. So pure imaginary numbers are just scalar products of I. So if you multiply c times I, that's really just 0, c. So here's how we show that the ordered pair x comma y can actually be written in the form x plus iy. So our starting point z is x comma y. Well, we can think of that as x comma 0 plus 0 comma y. I think that's pretty obvious that that arithmetic works out there, right? But then another way to write x comma 0 is just x, like we defined at the top of this page. And then 0 comma y, what we saw from our discussion of what a pure imaginary number is, that would just be y times I. Or if you want to write that the other way, x plus iy, that's fine too. So this is cool. So check it out. We have complex numbers now, and we're writing them the same way we did in the past, but nowhere have I ever had to say I is the square root of negative 1. In our formalism, I is just this point, 0 comma 1. So we're going to call the identity I squared equals negative 1 the fundamental complex identity. And with that piece in place, all of our complex arithmetic is going to become way easier now. We won't have to think about ordered pairs, and it'll be just like it was back when you were in pre-calculus. So why is I squared negative 1? Well, that's pretty easy to work out. I squared just means 0 comma 1 multiplied times 0 comma 1, because remember, I by definition is the ordered pair 0 comma 1. And then we have a definition for this doing this kind of multiplication. It would be 0 times 0 minus 1 times 1 in the first component, and then it would be 0 times 1 plus 1 times 0 in the second component. If this seems mysterious to you, just write down the formula for multiplication on a sheet of paper on the side here somewhere, and then just check that I'm doing it right according to that formula. But anyway, this simplifies out to negative 1 comma 0. And anytime you have an ordered pair of the form x comma 0, we identify that with the real number that's in the x component. So this is just negative 1. So voila, I squared is negative 1. But we never had to say I is the square root of negative 1, which seems like a weird thing to say. Okay, so now that we have the fundamental complex identity in place, we can go back to doing addition and multiplication the way that we always would have, in a sort of very intuitive arithmetic way, rather than using strange formulas defined in terms of ordered pairs. So for example, if I want to do the sum of z1 and z2, where z1 and z2 are defined, as x1 plus y1 times I, and then x2 times y2 times I. And of course, we're going to take c here to be just a real number as a scalar. To do that sum, z1 plus z2, I'm just going to combine like terms, right? Just like we did back in the past. So this would be x1 plus y1i plus x2 plus y2i. So I'm going to combine the real parts, and I'm going to combine the imaginary parts, which will give you x1 plus x2 for the real part, and then you'd get y1 plus y2 as the imaginary part. And then if we wanted to multiply complex numbers, we just FOIL it out like we did a little while ago. Z1 times Z2 would be x1 plus y1i times x2 plus y2i. And then, if you were not educated in the United States, you may not be familiar with this acronym FOIL, but it just means to multiply the first, the outer, the inner, and the last terms, and then add them together. So multiplying the first terms, you get x1, x2, and then multiplying the outer, you get plus x1, y2i. Then you get plus y1, x2 times I. And then the last term is going to be y1, y2, and then I squared. But we remember that I squared is equal to negative 1, so this becomes x1, x2, and then minus y1, y2. So I'm gathering the real parts here. And then the parts that have an I on them, I can factor out the I, and I would have x1, y2 plus y1, x2 times I. And if you compare this to our definition of multiplication in terms of ordered pairs, you'll see that this term is the first component of the product in that formula, and this term here is the second component of that formula. So it's the same formula, but you see here you get it more naturally because you're just distributing a sum over a product. And of course, to do scalar multiplication, you would just distribute like usual. So if you were going to do c times z1, that'd be c times x1 plus y1i. So that'd be cx1 plus cy1i. I think we've explained why this works here. So I think I'll just leave it at that. But the point is, we've moved away from needing to do things in terms of ordered pairs. So defining things in terms of ordered pairs was just an initial convenience to get around this uncomfortable discussion about what do we mean by I equals the square root of -1. So we ended up with I was just an ordered pair, 0, 1, and we never had to encounter that particular difficulty. But having worked around it, we're now back to sort of what your understanding of complex numbers might have been before you ever came to this class. So that's good. So now we can proceed on to doing some actual new stuff. Just a few examples here, just to make sure we understand how to do the arithmetic. If I wanted to do that first sum there, 2 plus 3i plus -1 minus 5i, so I would just add the real parts, and I would get 1, and then combine the imaginary parts, and I would get -2i. In the second part of this example, it's a product of two complex numbers, but, you know, I can just distribute like normal. I don't have to think about it in terms of those ordered pairs and then do that complicated multiplication formula. I would just distribute, and I would get I plus 8i squared. And anytime you see an even power of I, you can convert it to, well, if you see I squared, you can convert it to -1. So this would end up being -8 plus I. On this third example, I'll just FOIL things out, and I end up with 1 plus I minus I, and then minus I squared. You can see that the plus I and the minus I cancel out, and then you got 1, and then minus -1, so a grand total of 2. And on that last one, of course, that's just scalar multiplication, but in practice, I'll just distribute just like I did in the second part of this example. So I'd get 12 plus 6i. So easy peasy, right? At some point, we'll have to deal with division, and we'll want to define subtraction, I suppose, but we'll get there. So our next objective is to make sure that we understand all of the basic algebraic properties of the complex numbers. So these are often called field axioms. If you've taken abstract algebra, you might be familiar with the word field. So in abstract algebra, you study algebraic structures, groups, rings, fields, things of that nature. It turns out that the complex numbers form an algebraic structure called a field. And fields are very nice because they have lots of good properties that we use for doing things like solving equations and all that good stuff. So the complex numbers, we have these two operations, addition and multiplication. And then here are the properties that are true for addition on the complex numbers. The first property just says that if you add two complex numbers, you're always going to get back a complex number. That property is often called closure. The second property says that it doesn't make a difference what order you add two complex numbers in. So z1 plus z2 equals z2 plus z1. That's often called commutativity. The third property says that when you want to add three things together, you have to choose which two you're going to add at a time, right? So you can either add the first two things together and then take the result of that and add it to the third thing, or you can add the second and the third thing together and get a result and then add that to the first thing. It doesn't make a difference how you group things like that when you're talking about addition. So this property is called associativity. The fourth property just says that there's this special element that we call 0, that when you add it to any complex number, you get back that same complex number. Of course, we do have a 0 in the complex numbers. It'll turn out to be the ordered pair 0, 0, which we can represent as 0 plus I times 0, and of course we just call it 0. The fifth property says that if you start with a complex number, there's an additive inverse that you can add to it, which will yield 0 when you add it to the original number. So for every z, there exists negative z having the property z plus negative z equals 0. So this would be called an additive inverse. The fourth property, we call that the additive identity. And then we have similar properties for multiplication. So the first multiplication property there, M1, is that we have closure for multiplication. When you multiply any two complex numbers, you always get back a complex number. The second property just says that you can multiply two numbers in whichever order you want. It doesn't make a difference. You'll get the same result. So z1 times z2 always equals z2 times z1. So that's also called commutativity. The third property is again called associativity. Just says that when you're multiplying, you can group how you like. The fourth property says there exists a multiplicative identity. So there's a special number that we're going to call 1 that has the property that when you multiply 1 times any z, you get back z. The fifth property says that every non-zero complex number has a multiplicative inverse. In other words, for every z that's not equal to 0, so that's what we mean by that c/0 there. It means for every z and c minus 0. So z is not equal to 0. So for every complex number z that's not 0, there exists some other element, z inverse, we call it, having the property that when you multiply z times z inverse, you get back 1. So this is multiplicative inverse. And then lastly, there's the so-called distributive property. It just says that if you have z1 multiplied times the sum, z2 plus z3, that you can distribute z1 over the sum. These properties, these 11 properties, completely determine everything, all the other properties of complex numbers that we're going to derive. Everything comes back to this. Now, each one of these properties, they're all easily verified because it's just going to come from our definition of addition and our definition of multiplication. You can easily check any one of them. We're not going to go through and check all of them, but I think we should go through and check a few of them just to get a sense of how these things are verified. And then I think maybe for exercises or homework, you can do some of these. So let's check, let's see. Let's check A2. So A2, that was the property that addition is commutative. So we could check that pretty quickly. Now, by the way, we get to assume in this class that all the normal properties of real numbers are true. So it turns out that the real numbers are a field also and have corresponding axioms. So we know that addition of real numbers is commutative, and multiplication of real numbers is commutative, and that sort of thing. So we can assume all that's true. So for A2, what we're wanting to show is that z1 plus z2 equals z2 plus z1. So z1 plus z2 equals x1 plus iy1 plus x2 plus I times y2. And then based on our previous discussion, we know that the way that these numbers can be added is component-wise, or in other words, we can add the real parts and we can add the imaginary parts separately. And so doing that, we get x1 plus x2 plus I times y1 plus y2. We can take advantage of the commutative property for addition of real numbers and write this as x2 plus x1 plus I times y2 plus y1. But then when we look at how we just added things here, we see that this is exactly x2 plus iy2 plus x1 plus iy1, which is, of course, just z2 plus z1. So you see that what's going on here is that in this key step right here in the middle, we took advantage of the commutative property of addition of real numbers. So you can kind of think of the commutative property for complex numbers as being inherited from the real numbers. Okay, so A4, that was the existence of an additive identity. So what we want to show is that there exists some special element 0 in the complex numbers having the property that whenever you add 0 to z, you get z. Okay, so we can do that. So what should 0 be? I know this seems like a strange question. You're like, well, 0 is 0. But remember, we got to think about complex numbers as ordered pairs, or we can write in that equivalent form a plus b times I. So what should we set 0 to be equal to? Well, 0 is going to just be 0 plus 0 times I, right? If we take z equal to x plus iy to be an arbitrary complex number, then we see that if we do 0 plus z, that's 0 plus 0 times I plus x plus iy. And then when we add things the way that we know we're supposed to add them, adding the real parts and imaginary parts separately, we get 0 plus x plus 0 plus y times I. And then that works out to be, of course, just x plus iy, which is z. You can see what we did there. We proved that 0 plus z is equal to z. None of these proofs of the field properties for the complex numbers are terribly deep, but they do make you think about complex numbers sort of from scratch. So the tricky part is just sort of getting out of the way of yourself and not trying to work with stuff that you already know and trying to only work with the bare minimum things that you got from the definitions. Sometimes it's hard to do that. So M4, we're trying to prove the existence of a multiplicative identity. So we want to show there exists some special element 1 in the complex numbers such that 1 times z is going to be equal to z for every z in the complex numbers. Our 1 is going to be 1 plus 0 times I, right? Then for arbitrary z, we see that 1 times z is really 1 plus 0 times I times x plus iy. And then we know how to multiply things out, and we get 1 times x plus or minus 0 times y for the real part plus I, and then we have 1 times y plus 0 times x Let's see, so that works out to be x plus I times y, which is z. So there we have it. 1 times z is in fact equal to z. What a relief. Would have been bad if that was not the case. But anyway, we're getting these properties from first principles, so this is good. So we know that the complex numbers are a nice field. So M5, that is the existence of multiplicative inverses of non-zero complex numbers. So the property that we're wanting to prove here is that for every non-zero complex number, there exists some other element that when you multiply it times your z, you get back 1. This one is not quite as obvious, so we need to do a little scratch work before we do the proof to figure out what is this inverse. So let's have our z be x plus I times y, and let's have our z inverse. We don't know that it exists yet, but we're going to pretend that it exists for a little bit and then see if we can figure out what it would have to actually look like. But for the short term, let's just say z inverse is some other complex number. Let's write it as, like, say, u plus I times v. What we want is that z times z inverse is going to be equal to 1, i.e. x plus iy times u plus iv. We want that to be equal to 1. And of course 1, just for emphasis, I'm going to write it like that. 1 plus 0 times I. And then we can multiply this out on the left-hand side here. We need x times u minus y times v plus I times xv plus yu equals 1 plus 0i. Well, we know from way back at the beginning here, we said that when two complex numbers are equal, that just means that their real parts and their imaginary parts are equal. So I know that xu minus yv has to be equal to 1, and that xv minus yu has to be equal to 0. So from here, I have two equations. Xu minus yv equals 1, and xv plus yu has to equal to 0. Well, you see what this is? We're trying to figure out what u and v would have to be, because u and v are the components of the inverse. So we just want to solve this system of two equations and two unknowns for u and v. So if I want to solve this system of two equations and two unknowns for u and v, I can use the process of elimination. If I took the first equation and multiplied it through, so let's say I want to eliminate the v's, then I could multiply the first equation through by x, and then I could multiply the second equation through by y, because that'll give me negative x times y times v in the first equation and positive x times y times v in the second equation. And so if I do that multiplication and then add those two equations together, I'll get an equation with the v's eliminated. So what would that yield? X squared u plus y squared u equals x. And then I can solve for u, and I would get u is equal to x divided by x squared plus y squared. And similarly, well, I could do the elimination thing again, but another way I could go about this is just to plug what I have for u into one of the two equations and then solve for v. I think it would be easiest to plug into the second equation. So if I plug into the second equation, I'd get x times v plus y times u, which is x over x squared plus y squared, equals 0. And then I could just solve for v. So v would equal negative y over x squared plus y squared whenever I solve for v there. Because the x's are going to cancel, the x in the numerator of that fraction is going to cancel whenever I divide both sides by x. I guess I'd have to be careful about that and make sure I'm not dividing by 0. So to avoid that problem, I could just factor the x off at the beginning and then say either x, if x is 0, then this happens, and then, but anyway, this is what your v has to be. There's your v, there's your u. So in my scratch work, what I'm learning here is that my z inverse, which is, remember, u plus I times v, is this x over x squared plus y squared plus negative y over x squared plus y squared times I. So through my scratch work, I know what my inverse has to be if such a thing exists. And so now I can do a formal proof, having done the scratch work. Let's do our proof now. Okay, so for our proof, we just start with some arbitrary z. We'll call it x plus iy, and suppose that it's in the complex numbers minus 0. Now, one little subtlety that we need to think about is that in our formula that we derived up there in our scratch work for z inverse, you see that we got those fractions where the denominator is x squared plus y squared. We just want to make sure that that's not equal to 0. But since the z is not equal to 0, we know that x squared plus y squared is not equal to 0. Because if x squared plus y squared were equal to 0, that would mean that both x and y have to be 0, but we know that both x and y are not 0. Okay, so having established that, then we can just sort of pull out what we think z inverse is. So let's say let z inverse equal this magical quantity that we found a minute ago. And then what do we need to prove about this thing that we're calling z inverse? We need to prove that it has the fundamental property up here that when we multiply it times the original thing, that we get 1. We also need to point out that it's a complex number. Well, since x squared plus y squared does not equal to 0, we see that z inverse is in fact a complex number because the real part and the imaginary part are just regular old real numbers, right? Also, if we do z times z inverse, that would be x plus iy multiplied times what we're claiming z inverse is. So x squared plus y squared plus negative y over x squared plus y squared times I. And of course, we know what we're going to get. It's sort of preordained, but let's just go ahead and check it. Multiplying the first terms, we get x squared over x squared plus y squared. Multiplying the outer terms, we get minus xy over x squared plus y squared times I. Multiplying the inner terms, we get plus xy over x squared plus y squared multiplied times I. And then multiplying the last terms, we get plus, there's like a minus y squared in the numerator. Then we get x squared plus y squared. And then there's I times I, so we get an I squared. And if I get my canceling stick out here, I see that this whole term cancels with this whole term because they're just opposites. I squared there is the same as negative 1. So really I've got positive y squared there on that last term. So when you combine like terms, this just works out to be x squared over x squared plus y squared plus y squared over x squared plus y squared. I can combine those into one fraction, which would be x squared plus y squared over x squared plus y squared, which of course equals 1, like we knew it was going to be. But the upshot here is that we found the inverse of a non-zero z, and we checked that when we multiplied it times our original z, we got back 1. I think I've already been using subtraction in this lecture, but we actually haven't really defined subtraction yet, so I guess we should be a little careful here and say, what do we mean when we subtract two complex numbers? So the definition of z1 minus z2 is really we just define it as adding the additive inverse, right? So this is z1 plus negative z2. See, we know that negative z2 exists because of the axioms, the existence of an additive inverse. So this is how we define subtraction. Subtraction is really just a form of addition, right? And similarly, we can define what we mean by division of complex numbers. So we so far don't have an operation of division defined for complex numbers. But of course, we now know what multiplicative inverses are, so we can just define that quotient to be z1 multiplied times z2's inverse. Now you got to bear in mind, z2 raised to the negative 1 doesn't literally mean 1 over z2. Now it's going to turn out to work out that way, but that's not definitionally what z to the negative 1 means. It means the multiplicative inverse, the number that you multiply times z2 to get back 1. But luckily, everything's going to work out in, to be the way that you're used to, where z2 to the negative 1 really is 1 over z2. But for now, I just want to point out that we have a certain formalism in place that doesn't include 1 over z2. So we could work out that, like what z1 over z2 is as some sort of like formula in terms of the real and imaginary components. But that's really unnecessary because really we already know how to do division if we actually need to perform division, because we've all learned that trick of multiplying by a conjugate. Like whenever you were in pre-calculus or some class like that, maybe high school algebra, your teacher probably always told you to not leave radicals in the denominator. There's actually nothing wrong with having radicals in the denominator, but you can clear them by multiplying by conjugates. And when we see that I down there in the denominator, we know that we can clear it by doing the same trick. So if I started with 2 minus I divided by 4 plus 3i in this first example, well, I can do the trick of saying, well, this is really just 2 minus I over 4 plus 3i, and then I can multiply by that conjugate of the denominator, so do 4 minus 3i over 4 minus 3i. And the reason we're doing that is it'll get rid of the I in the denominator. And by the way, we're really just multiplying by 1 here, right? So it's always okay to multiply by 1. But when you perform this multiplication, then what do you end up with? Well, you multiply out in the top and you get 8 minus 6i minus 4i plus 3i squared. And in the denominator, you get 16. Then you're going to get a minus 12i and a positive 12i. So those cancel, and then you end up with minus 9i squared. And then you can simplify all this. So this is, in the numerator, you've got 8 minus 3, so that's 5, and then minus 10i. And in the denominator here, you've got 16 minus 9i squared, so that's really plus 9. So it's divided by 25. And if you like, you can write that as 1/5 times 1 minus 2i. The thing that we're talking about up here and how we define division really isn't all that helpful in actually performing division. It just gives division a formal definition so that if we're doing a proof, we know how to handle it. But the actual process of doing division is sort of divorced from that. Now, I would get the same result here if I went and I took the denominator and I found its inverse according to the formula that we had a minute ago, and then multiplied it times the numerator the way the formula says. You'd get the same answer. It would just be a bit more work. Okay, so now that we have the 4 operations in place, so we'll see that our arithmetic conforms to the usual notational conventions that we use in real number land. So 1 over z, of course, according to our definition of division up there, that's the same as 1 times z inverse, or just z inverse. So 1 over z really is z to the negative 1. So that's good. Of course, we already said this one. If we want to write a division as a product, we can just definitionally write z1 over z2 as z1 times z2 inverse. This last one, how do you do on the third one here? We could ask, what is z1 times z2 inverse? And we kind of know what we hope the answer is. We hope that we can distribute the exponent. Well, I claim that this would actually be z1 inverse times z2 inverse, like this. And you can verify that this is true, because whenever you say z1 times z2's inverse is this other thing, it means that when you multiply z1, z2 times that thing on the right-hand side, you should get back 1. So if I take z1, z2, and then multiply that times z1 inverse times z2 inverse, well, we know that we have commutativity and associativity in multiplication, so I can group the z1 and the z1 inverse together, and the z2 and the z2 inverse together. And then, of course, by the definition of multiplicative inverse, I get 1 times 1, which is 1. So anyway, all the usual sort of tricks for doing arithmetic go through when you're doing complex numbers. I mean, that's what's great about complex numbers. It's basically all your intuition about how you do algebra, how you do arithmetic, that you already know for real numbers. Every bit of it works. But then there's some advantages. In the complex numbers, you have a little bit more structure that you can take advantage of. So actually, the complex numbers are a bit more complete than the real numbers, but it's good that all your intuition doesn't have to go away. So here's a formula that you may have seen before. It's called the binomial formula. The proof of this is left as a homework exercise. But I just want to show you how it works. It's a little bit scary looking. It's called the binomial formula because z1 plus z2, that's something that we would call a binomial. It's, just an expression with 2 terms. And then when you raise that to the nth power, you get this crazy looking sum on the right hand side that involves n choose k and different powers of z1 and z2. There's kind of an easy way to apply it without really thinking about that formula too literally. You can make a little triangle, start with 1 on the top, and then put 2 1s below. And then to get terms below this, you always just, it's always 1s down the side. But I'd put a 2 here because it's the sum of the 1 and the 1 above it. Here I'd have 3, 3, 1 because I'm adding, and so on and so forth. I think this is called Pascal's triangle or something like that. Well, you can see how it kind of continues forever. Each place down below, if there are 2 numbers above it, you just add those 2 numbers above to get the number below. And the first line of this table corresponds to when n is equal to 0. The second line is when n is equal to 1, and n equals 2, n equals 3. So to do this example that I have here of doing 3 minus 2i to the third power, first of all, let me think of that as 3 plus negative 2i to the third power. And then the way the binomial formula would be applied is you take this third line here, and those would be the coefficients that you're going to have from the binomial formula. So Pascal's triangle gives the binomial coefficients, it turns out. So the first coefficient would be 1, and then it's times your z1 term to the maximum power. If you want, you can put the z2 term there. Well, the z1 here in this case is 3. That's to the third. And then you can have your second term, 2i to the 0 power. Plus, then you take that next coefficient in yellow over there, and then you do the first term in the binomial, so it's 3. That'll be to the second power. Then you have that negative 2i to the first power, so the exponents are coming up on that term. Then you'd have 3 times 3 to the 1 times negative 2i to the second power. And then you would have 1 times, then you'd have 3 to the 0, and then negative 2i to the third power. So if you simplify all that, you get what 3 minus 2i to the third power is. So it's actually not as bad as it looks. So you'd have 27 from the first term. Let's see, you got 27 times negative 2, so negative 54i from that second bit. And then you're going to have plus 3 times 3 times 2, 18. So you get an I squared there in that third term. So you just end up with 3 times 3 times positive 2. And then on the last one, you have negative 8 times I cubed, so that'd be positive 8i. For this term, you're really getting, you get like negative 8 times I cubed, but then that's negative 8 times I squared times I. And that negative 8 times I squared is just positive 8. And then you combine like terms. So 27 plus 18, I guess 45. And then looks like minus 46i. So there's the binomial formula. This formula is convenient, for example, when you're dealing with formulas involving general nth degree terms. In particular, a little later when we're wanting to do the derivative of z to the n, this formula will be useful for that. Okay, one last thing that needs to be mentioned about the complex numbers is that the complex numbers are what's called an integral domain. That just means that the complex numbers have this special property that's really nice. If you multiply two complex numbers and you get 0, then it's got to be the case that one of the two numbers, at least one of the two numbers, is 0. Without this property, it's pretty hard to do equation solving, or at least it becomes a lot harder. I want to prove this. Before I prove it, though, I want to remind you of a little bit of logic from your foundations class. So it turns out that a statement of the form P or Q is logically equivalent to a statement of the form not P implies Q. Anytime I want to prove an or statement, a way that you can prove that is to suppose that one of the two terms in the or statement is false and show that that forces the other one to be true. So with that in mind, let me start my proof over here by saying, let z1, z2 be complex numbers. And suppose that z1, z2 is equal to 0 with z1 not equal to 0. So we're trying to prove that z1 equals 0 or z2 equals 0. And here I am supposing that z1 is not 0. So what we got to prove is that z2 must be 0. Taking advantage of this logic over here. What do we know about complex numbers that are not 0? Well, since z1 is not 0, then we know that z1 inverse exists. Now we can take advantage of that, because from this, I can certainly say that 0 is equal to z1 inverse times 0, right? 0 times anything is 0. But we know that z1 times z2 is 0, so I could make a substitution here. And now I can use the associativity property to write this as z1 inverse times z1 multiplied times z2. But then that's just 1 times z2, which is z2. So what have we shown in total here? We've shown that 0 is what z2 has to be. And that completes the proof. You use this property a lot when you're solving equations, right? And like you got something like, x squared minus 1 equals 0. And then you factor on the left-hand side and you get x minus 1 times x plus 1 equals 0. And so you go, oh, that must mean x minus 1 equals 0 or x plus 1 equals 0. And then from there you would get to like, well, that means x equals 1 or x equals negative 1. So it's a pretty important property to have if you want to solve equations using sort of the standard techniques that you've already learned from, dealing with real numbered equations. You can still use all your standard tricks for solving equations. Okay, I think I'll stop there, and we'll talk to you again in another lesson soon. Bye now.